Alright, welcome to Chapter 2, our first slideshow of this chapter. This one will be on atoms, molecules, and ions. This particular lecture will focus in on the atoms. So, beginning with John Dalton's atomic theory, we have that each 4 parts of his atomic theory, broken down this way. Each element is composed of extremely small particles called atoms, which sounds familiar. An atom of an element of oxygen we have there, and an atom of nitrogen. All atoms of a given element are identical, but the atoms of one element are different from the atoms of other elements. We know this still to be true. So all the oxygen atoms are the same, and all the nitrogen atoms are the same, but they're different from each other. So, come to number 3. Atoms of one element cannot be changed into atoms of a different element by chemical reactions. We can't just magically go from oxygen to nitrogen. It doesn't work. But atoms are neither created nor destroyed in chemical reactions. And this still holds true. And number 4 in his atomic theory is that compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kinds of atoms. So if you take nitrogen and oxygen and make nitrogen monoxide, we form a compound, they're bonded together, and it's always one nitrogen and one oxygen to form that particular compound. And this, again, still holds true. Over the years, there were discoveries that were made to add to our atomic theory. I'm going to highlight a few of them and what they led to, and then we will go into our modern atomic theory. So, the first experiment was the cathode ray tube experiment. CRTs, or cathode ray tubes, are what was used in the old televisions that you might still have lying around the house with a big back on them. Those have cathode rays in them. Well, a cathode ray it's produced in a vacuumed container, so this container is vacuumed out, has no air inside of it, and it says that our electrons move from the cathode, the negative end, to the anode, which is our positive end. Kind of like, alright, so our cathode ray tube also has this glass screen inside of it, so that we can see the beam that's created across it. So you get this line. It fluoresces or lights up when it has something excite it and hit it, like the cathode ray. So what they did was expose a magnet to this cathode ray tube, and it was found that the negative end of the magnet, or negative pole of the magnet, caused the rays to be deflected or pushed away. And when the other end, the positive end of the magnet, was exposed to the cathode ray tube, it attracted this beam. And this showed that our particles were negatively charged, because when you have a magnet that's positive and it attracts something, it means that other thing is negative. So, that is our cathode ray tube. Now, when they figured out that these particles were negative, showed us that atoms have their first subatomic particle, and it's negatively charged. And we all know that particle now to be called the electron. So that was our discovery of the electron. The next thing that was discovered in the structure of the atom was through Ernest Rutherford's gold foil experiment. So over here we have this setup of our gold foil experiment. The first thing is that we have this source of alpha particles. So inside this lead block is a radioactive material, and it's giving off alpha particles. Alpha particles are made of 2 protons and 2 neutrons. So they have a pretty good mass to them. And it had one hole in this thing, so it allowed only those alpha particles to come out of here, and it was directed at a piece of gold foil. Now this gold foil was very, very thin, so they wanted to see what would happen to these particles as they hit this gold foil. And what they also have in this experiment is around the gold foil is this fluorescent screen, so that if anything hits it and it's has energy, it will light up in those spots. So they shot this beam of alpha particles at the gold foil, and we found that most of the places where the fluorescence, the screen got excited was directly behind the gold foil, which means that most of the particles went straight through the gold foil. But some of them were deflected. They went at crazy angles and even got bounced back towards the beam. So this meant that they hit something, and that something had to have a dense mass to it. They were bouncing off of something. And since they did bounce off, it also meant that whatever the particles hit, it must also be positively charged. They knew that the alpha particles were positively charged because they had done other experiments to verify that. And so if these alpha particles were positive and they bounced off of something, it had to also be positive, whatever that something was. Well, they ended up naming that something, that positive, dense center of our atoms, they called it the nucleus of the atom. So if we have a screened in shot of this gold foil, we have our atoms of the gold here, and we can see most of these lines, which represent those alpha particles, they go straight through to the other side, but a few of them are deflected because they hit that positive mass in the middle there. So those ones show that they're bouncing off and hitting that positive nucleus. There's our nucleus of the atom. So we have electrons and we have a nucleus. We're on our way to finding our mono. So jumping ahead a little bit, since Rutherford's day, physicists have discovered and learned a lot about the atom structure, but as chemists, we keep it simple. We don't have to go into a lot of quantum theory and all that stuff. We don't need to know what makes our protons and neutrons and electrons. We just need to know that those exist and where they are and what kind of charge they have. So our atoms consist of protons and neutrons in the nucleus and electrons that occupy the electron cloud outside the nucleus. We call it an electron cloud, and we will discuss later in another chapter where in the electron cloud those electrons live and how they're structured. Alright, so in this table it kind of breaks down a couple pieces of information. Our protons have a positive charge and it shows their mass 1.0073, and we have neutrons, which are neutral, also in the nucleus, and they have a slightly bigger mass than protons, but not really much to make a big deal over. And then our electrons, they are negative, and they have a mass of 5.486 times 10 to the negative 4. So that's 0.0005. So comparing that to these other ones, our electrons are very, very tiny compared to protons and neutrons. So tiny that they barely contribute any mass to our atoms. So looking at this, our mass is in AMU. If you haven't heard of those before, AMU is atomic mass units. So it's the unit that was used instead of grams. So one atomic mass unit is 4 times 10 to the negative 22nd grams. Very, very tiny amount. So atomic mass units are used because measuring masses of atoms and subatomic particles in grams is kind of impractical. We're not going to set one single atom on a balance and measure in grams. So if the masses of atoms are expressed in AMU, we're speaking of a single atom. If we look at the mass on a periodic table and express that mass in grams, then we're actually talking about a mole of those atoms. So we have two different scales, either AMU when we're talking about a single atom, or grams when we're talking about a mole of atoms. Right, atomic size. So talking about our diameter, our size of the atom, we have some ways of measuring it. The size of an atom is quite small, and it's on the scale of 1 times 10 to the negative 10 meters to 5 times 10 to the negative 10 meters in diameter. So really it's, again, an impractical measurement. So the angstrom was developed to make this measurement easier. So 1 angstrom, so remember this is measuring distance, is equal to 1 times 10 to the negative 10 meters. So atoms are in the nano or pico range in the metric system. That 10 to the negative 10 meters is in between nano and pico. So we're getting, it's very, very small. So the diameter of the nucleus, so within that atom, is about 10 to the negative 4 angstroms. So it's just a fraction of the diameter of the atom itself. It takes up really almost no space in there. So if we want to get this kind of on a scale that we can understand, I have an example here. Let's imagine a hydrogen atom. So a hydrogen atom is one proton in the nucleus and one electron in our electron cloud. If we blow up that atom so we can actually see inside and walk around inside of that atom, okay, our scale is going to be a football stadium. So if the diameter of our atom was the size of a football stadium, like Bulldog Stadium at Fresno State, the nucleus, so the very center of it where our proton lives, would be the size of a small marble in the very, very center of Bulldog Stadium. So imagine you're sitting up in the stands. You probably couldn't even see the nucleus when it's sitting down there on the field. It's so small. The sphere around that marble, so if we thought of the marble as our center and a sphere completely around it, the size of that stadium, in that sphere we would have one tiny electron flying around, and it would be smaller than that nucleus, smaller than that marble, so small that we wouldn't even be able to see it flying around. And it would be flying around in all of that space because it can. So the size of the atom is just insane, and most of it is really just empty space. Where that nucleus is and where that one electron is the only things that are physically taking up space. The rest of it is just empty. It's kind of crazy. So when we're looking at atoms, we need to be able to figure out how many of these protons, neutrons, and electrons there are. So we have some numbers we deal with. We deal with our atomic numbers, our mass numbers, and that helps us lead into what are called isotopes. So the atomic number, it's our large number on the periodic table square, and it identifies that element. So carbon is element number 6, and it represents our number of protons. So carbon has 6 protons. In a neutral atom, this number also represents the number of electrons in that atom. So it has 6 protons balanced by 6 electrons, making 6 positive, 6 negative, and it's neutral. Alright, our mass number. So we have the average atomic mass on the periodic table, and we're going to talk about how that's calculated later. But when we're talking about a single atom, we have what's called the mass number. So often we use this symbol to represent an element. We have carbon, its symbol there. We have its 6 protons here, so it's atomic number. And then we have the mass number on the top, which is our protons plus neutrons. So if we add those together, we get 12. So if we have 6 protons, then we know we have 6 neutrons as well. And this is just our symbol, another way of writing the element. And then we have isotopes. So this is also the symbol for an isotope. This is the carbon-12 isotope. And an isotope is an atom of the same element with a different number of neutrons. So this particular isotope has 6 neutrons, but we can have different numbers. So this table shows our different isotopes of carbon. We have 4 different isotopes. So we've got carbon-12, the one we just looked at, so 6 protons, 6 electrons, 6 neutrons. Everything's balanced. Our first isotope of carbon, though, again, has that 6 protons. These will all have 6 protons because that's what identifies it as carbon. Again, they're all neutral, so they all have 6 electrons. But that carbon-11 has 1 less neutron, only has 5. Carbon-13 has 1 more neutron, and carbon-14 has 2 more neutrons. So we can make different isotopes, even though they're all carbon, they're slightly different masses because they have different numbers of neutrons. Now, 99% of the carbon found in nature, naturally occurring, is carbon-12. It's our most common form of carbon. So, try this one. How many protons, neutrons, and electrons are in a barium-138 atom? When we read these, we always read the element name first and then its isotope number. So barium-138. If you press pause now, you can try it out and then press play and I'll give you the answer. So, our answer for this one are protons. If you look on the periodic table, barium is element 56, so that's how many protons we would have. If it's neutral, then we would also have 56 electrons. And if we want to find our number of neutrons, we take its isotope number, 138, subtract 56 protons, and we get our 82 neutrons. So we can see that the neutrons are really that part that changes quite drastically. All right, there. So we have mass numbers. Now, average atomic mass, the number that's on our periodic table, is not the same as our mass number. The average atomic mass is going to be a weighted average of all the masses of our isotopes of that atom. So let's look at how this is calculated. Our equation is that the average atomic mass equals, the symbol is a sigma, it means sum of, so the sum of the isotope's mass times the percent abundance. Now the sum tells us that there are going to be multiple of these to add up. So we're going to take each isotope's mass and multiply it by that isotope's percent abundance and then add it to the other ones. So an example of this for chlorine. So chlorine, naturally occurring chlorine, is about 75.78% chlorine 35, so this isotope. And that isotope's mass is 34.969 atomic mass units, AMU. The other 24.22% is chlorine 37, and its mass is 36.966 atomic mass units. So we have two isotopes. We have their percent abundance and we have their mass, and we're going to calculate the average atomic mass of chlorine. So to set up this equation, we're going to plug it into what we have above. So the isotope's mass comes first, and we multiply it by its percent abundance. So for the first one, we have the mass of 34.969 multiplied by its percent abundance. Now, percentages, we always move that decimal over 2 places to the left and multiply. We're dealing with percentages. So we have that first one, and then again it's a sum, so we're going to add it to the other isotope. Its mass is 36.966 multiplied by its percentage. Again, we move that decimal over. So if this is all calculated, then we end up with 35.45 AMU, atomic mass units. This is rounded to 4 significant figures. If we look back at our problem, we have 4 significant figures in our percentages, so those are our lowest numbers of sig figs. So we round to 4 significant figures. Now, if we looked at a periodic table and looked at chlorine, its mass that's reported would be about 35.45. That's how they figure those numbers out. So tons of research has been done to find all the naturally occurring percent abundances for each element, find the mass of their isotopes, and do these calculations. Alright, looking at our periodic table, some reminders of how it's used. We have our groups or families, so these are the vertical columns on the periodic table. I also say, or chunks. So if we look at, say, the center chunk where it's the B group, we call those the transition metals. That would be a group. Or we can look at individual columns, like this last column we call the noble gases. So those are our groups or families. We have periods. So elements within the same period are horizontal rows. We have 7 different periods on the periodic table. And then we also have the stair-step line over here. So we have this line, and it separates our metals from our non-metals. Our metals are the left side of the periodic table. If you can't remember that, think of a common metal, like gold is a metal. Find where gold is. AU. It's on the left. So everything it's with on the left over here is a metal. Things you don't even think are metals, like potassium in bananas. Yes, you're eating metal. Okay? Then we have the other side, which is our non-metals, all the blue ones. Hydrogen is included in the non-metals. And then these purple ones, that sit along the stair-step line are our metalloids. So those are the ones that have properties of both metals and nonmetals. For instance, silicone has reactions similar to the nonmetals, but it conducts electricity like metal. So it's a metalloid. Now, we do have this weird setup down here that tends to confuse people. This bottom section, the inner transition metals, it always has a separation here. It goes from 56 to 71. Well, what happens to 57 through 70? They are down here in this first row on the inner transition metals. And we can actually take that bottom section and put it into the periodic table, and it would look like this. So those fit in the periodic table just like that. It's a little bit funky, but it works. And you can see it kind of stretches out our periodic table, makes it hard to fit on a piece of paper, does all kinds of things. So we always write it with it down below. But it does fit into our periodic table like that. So that is the end of this one. Make sure you review your atomic structure and know our different parts of the atom, how to read your periodic table squares, and where to find information on your periodic table. This will save you more time than you can ever imagine in this class if you can use that periodic table.